Okay, so we want to spend a little bit of time looking at organic chemistry, just a brief overview, because it is a really large part of chemical reactions. So first of all, why does carbon get its own branch of chemistry? So in order to understand the answer to that question, you have to understand some things about these compounds. First of all, the carbon-based compounds or organic compounds are the basis for all life. And these compounds are basically comprised of carbon atoms, which are unique in the fact that they can form very stable covalent bonds to other carbon atoms. So you have single, double, triple bonds. You also have long chains. You also have rings. So because of this, you have a huge number of compounds, and that results in an entire branch of chemistry. So just to explain a little bit more, we start off by looking at the hydrocarbons, which are basically hydrides of carbon. And the main feature of these is that you end up with long chains. So we simply classify these hydrocarbons, which only contain carbon and hydrogen and only have single bonds, as alkanes. And then we have a system of naming them whereby the prefix comes from the number of carbons. So one carbon is meth, two carbons eth, three carbons prop, four carbons but, five pent, etc. So instead of drawing out these covalent bonds, we also have a shorthand way of representing the structural formula, which is called the condensed structural formula. So basically, you list all the atoms, but you just show the order that they're bonded in without showing the covalent bonds. So it's just a convenient format, and you have to be comfortable going between the two representations of the structure. The other thing you have to recognize is that once you have four or more carbons, you now have what we call isomers, which means you have compounds with the same molecular formula but a different arrangement of atoms. So, for example, if you have C5H12, there are three different arrangements. You can have all five carbons in a straight chain, which would be pentane, or you could have four carbons in a straight chain with one carbon branched off of one of the middle. That would be 2-methylbutane. Or you could have three carbons in a straight chain with two carbons branched off of the middle one, which would be 2,2-dimethylpropane. These isomers would have different properties and behave differently, but they would all be what we call isomers. The other thing that you should recognize as well is that there are sometimes representations whereby you omit the carbon atoms because there's so many of them, and so you know that they're at the end of each line segment, and each line segment just represents the covalent bond. And then you don't even really show hydrogen at all. You don't show the bond to hydrogen, and you don't represent the hydrogen atom. You just show whatever it is that's special about that particular molecule. Other models include the ball and stick and space filling. These models give you the three-dimensional representation. So going back to our simplest hydrocarbon, we said we only have hydrogen and carbon, they only have single bonds, and you would have the general formula CnH2n plus 2. So this would help you to identify just by looking at the formula if you have an alkane. Again, the first four members of the alkanes, the prefix would come from the number of carbons, and we refer to this as a homologous series because each successive member of the series only differs by one carbon or by a CH2 group. In general, the physical properties of alkanes, they are nonpolar, so generally not soluble in water. They're low density, low melting point, low boiling point because of very weak attraction between these nonpolar molecules. As you can see though, as the number of carbons increase, you have an increase in the boiling point and melting point. We'll talk about that much later on, but it has to do with the increase intermolecular attraction between the molecules that increases with increasing molar mass. Where do we get alkanes? Mostly by refining or by hydrogenation of petroleum, coal. Low molecular mass alkanes are obtained from natural gas as a result of the fractional distillation. Some reactions involving alkanes, one of which should be familiar. Combustion is very common, right? We use these alkanes as fuel. They produce a tremendous amount of energy. We use them in gas grills, lighters. We use them in Bunsen burners. Less common would be the reaction whereby halogen can replace one or more hydrogens. This can occur in the presence of heat or light. This process is used to prepare solvents such as paint stripper, chloroform, dry cleaning fluid. So we talked a little bit about the naming system with the prefixes. What I wanted to talk a little bit more about is where things become a little bit more complex. So these are the prefixes that you would have to know to name these organic compounds. If you're naming alkanes, you just identify the longest chain, count the number of carbons, use the prefix, and then end with the ane ending. Any branches on that chain, you would name that branch, but give it a YL ending. And then if you have more than one of the same type of branch, you would then say di or tri to represent having 2 or 3 of them. And then you would give numbers to indicate the location of each branch. Let's just practice that. Let's say you had this compound. We're leaving the hydrogens out because it just makes it simpler at this stage. How many carbons do I have in my straight chain? 6. So that means the prefix is going to be hex. Because they're all single bonds, it's going to be hexane. So that's the name of the compound, hexane. What about this one? How many carbons are in my longest straight chain or consecutive chain? 5. So my prefix will be pent. All single bonds, so it's pentane. Now there's a single carbon, which is a meth group, branched off of the second carbon of that chain. So it would be 2-methylpentane. Can you do these? Let's start with this one. Where's my longest chain? Notice that my longest chain is actually not from left to right. I would start here, 1, 2, 3, 4, 5, 6, 7, which is heptane. And then I would call this 1, 2, 3, 3, 4, 5, 3, 5 dimethylheptane. What about this one? Where's my longest chain? In this case, it doesn't matter if I count from left to right or curve here. It's exactly the same. 1, 2, 3, 4, 5, 6, 7. So it's heptane, but I have an ethyl group on the third carbon and a methyl group on the fifth carbon. So 3-ethyl, 5-methylheptane. What about this one? Again, be careful. This is not my longest chain. My longest chain would come from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is decane. and I'm going to count all of these as if they're branches. Uh-oh. So I've got 3, 4, 7, 3, 4, 8, 9, 3, 4, 8, 8, 9 tetramethyl. If I count from the other side, I can use lower numbers. So 2, 3, 3, 7, 8 pentamethyl decane. This is the condensed structural formula, but it might help you to convert it into the carbon skeleton and then be able to count from there. Can you name it now? 1, 2, 3, 4, 5, 6, so hexane. 2, 5 dimethyl hexane. We also have alkyl halides, which would be very similar, except now you would have to name the halogen just as you would if it was a branch. What happens if you have a multiple bond between carbon atoms? Then you have either an alkene or an alkyne. Here's some ball and stick models. Ethane, ethene, which has a double bond, or ethyne, which has a triple bond. Naming alkenes and alkynes, if there are more than 3 carbons, you do need to indicate the location of that double or triple bond. And the multiple bond will take priority when determining how you're numbering those carbons. I'll end here for now. I hope this was helpful.